Okay, so last class we learned about the various types of forces as well as the force of gravity and how to calculate the force of gravity between any two objects with that equation and Newton's law of universal gravitation. Today we're going to be talking about how to calculate any force and any force between two objects besides just gravity. So our topic for today is forces in free body diagrams. Your objective is to be able to determine, describe, and calculate the various forces on an object. Your essential question is, what is the total amount of force acting on an object? So you, after reading these notes and taking these notes today, should be able to answer this essential question in your summary. What is the total amount of force acting on an object? You should read that essential question again, read through your notes, and then answer that essential question about 1 to 2 sentences in the summary at the end of your notes. All right, so let's first review our definition of what a force is. Now, a force is a push or a pull. Again, as simple as that. The variable that we use to represent force is a capital letter F. Our unit of measurement is newtons, which we shorten up to be just an uppercase N. Short for newtons, again, after Sir Isaac Newton. An example of a force, we've talked about this from last class, applied force, gravity, friction, air resistance. These are all different types of forces acting on an object at any given time. So here's our new equation that we will be talking about today. So in order to calculate the force acting on any object at any given time on Earth, let me specify that that is on Earth, we multiply that object's mass. And remember, mass is measured in kilograms. Multiply that times that object's acceleration. And remember, acceleration's units are meters per second squared. So mass times acceleration is equal to the force of any given object. All right, so we are going to practice using that equation now. Get back to here. All right, so if we're using this equation, let's work out this example here. A box with a mass of 10 kilograms sits still on a table. What is the weight force of the box? So we're going to follow our 5 steps to solving a physics word problem here. And I'm going to zoom in a little bit so we can see this example a little bit better. Okay. All right. So here is our picture. That is step number 1. Remember, step number 1 for solving any physics word problem is to draw a picture. And I'm also going to label this box as 10 kilograms, meaning its mass is 10 kilograms. No, I'm not going to make that an arrow, actually. Okay. So that is step number 1. To draw a picture. All right. We also know, according to our different types of forces, that the forces acting on this box right now are the force of gravity, aka our weight force. So Fg, that's equal to our weight force. And see if you can remember what Fn is equal to. So Fn is equal to our normal force So remember, our normal force is the force exerted by that surface that an object is sitting on. So the normal force in this case is the force exerted by the table that the box is currently sitting on. Okay, so there's our labeled picture here with our forces. All right, so step number 2, again, is to make a T-chart of what we know and what we don't know. And I'm just going to write IDK for don't know. All right, so a box with a mass of 10 kilograms. So right off the bat, it's saying, all right, our mass is 10 kilograms. So I'm going to actually make this different color. All right, so here's one thing we know. And in this color, I'm going to write M for mass is equal to 10 kilograms. Okay. Sit still on a table. What is the weight force of the box? All right, so let's skip over something and I will highlight this thing. This is our force that we are solving for. Actually, I'm going to highlight this whole thing. So we are solving for the weight force. Okay, so I'm going to write that in here, Fg, that's our weight force, is equal to question mark. So according to our equation, we are missing, we don't have F, we have M. We need to figure out what the acceleration is in order to solve for F. So let's move back over to our problem here. So think about the one thing you always know, something, a constant that you will always know on Earth. Now, if you remember correctly, the constant that we always know is G. So we always know that G is equal to negative 9.8 meters per second squared. So G, remember, is our acceleration due to gravity. So there's our acceleration right there. It's G when we are solving for weight force. Remember, your weight force is the force of gravity acting upon you due to your mass on Earth. So we are just substituting acceleration, which could be any acceleration for a different type of force, with the acceleration due to gravity. So your weight force is actually always going to be calculated using this equation here, F equals mg. And we will always know G. Because this is our constant. All right, so that is our weight force. I'm going to specify Fg is equal to mg. So there's our step number 3. Step number 4, we are actually ready to plug in. Fg is equal to the mass, which is 10 times G, which is negative 9.8. If you multiply those together, you should get a force of gravity, or the weight force is equal to negative 98 newtons. And again, that negative sign is important. That indicates that negative 98 newtons, or you are negative 98 newtons, acting on the surface of the Earth. So there is your weight force there. That is how we calculate any given force. So specifically weight force, but again, F equals ma would be how you calculate any given force on acting on an object. All right, so again, any object could have a variety of forces acting on it at any given time. So to represent these different types of forces acting on an object at any given time, we draw what is called a free body diagram. So a free body diagram is a drawing that depicts all of the forces acting on an object at a point in time. So we have a series of steps we need to follow to draw a free body diagram, which is FBD is short for free body diagram. So let's work out these steps. We'll work through these one by one. The first step to drawing a free body diagram is to draw a picture of the scenario. So I've already done that for you all. We've got a scenario. You are on a moving ramp. You're pushing a box down the moving ramp, right? The second step is to simply circle the object in question. So the object in question right now is the box. We want to know what forces are acting on this box as you push it down this ramp. All right, so we should make a list of all the potential forces that could be acting on the box. So we already know you are pushing on that box. So we do already have an applied force. All right. We also know that the force of gravity is always acting on that box. So we also know we have a weight force. I'll give you a hint. Any object on Earth is going to have a weight force, right? This object, this box is on a surface, so we are going to have a normal force. That normal force exerted by that surface. And remember, the normal force is perpendicular, so it's at a right angle to the surface, right? And we are also going to have friction. So friction, remember, is that opposing force to movement. Since we are pushing that box down a ramp, unless it's like an ice ramp, but even ice has some friction, this ramp is going to have some friction as you push this box down. So here's our list of all the forces that could be acting on that object. All right, so in order to map this out, you are going to replace that object with a dot. So I've got my scenario here, and I'm going to take that circled box and say, you know what? Let's just make this a dot. This is our box. That's our box now. All right, that's just a little bit easier for us to draw. And we also see all the forces acting on that box now. So step number 5 is to draw arrows away from the dot, which is our object in question, our box here, to represent the magnitude and direction of each force. So here's a key point here. The direction of the arrow indicates the direction of the force. The length of the arrow indicates how strong or the magnitude of that force. Okay, so let's say that you are super, super strong. So we're working with a really strong applied force. So I might draw an extra long arrow on that applied force and label that FA. All right, so that means you are really, really strong and putting a lot of good force into there. All right, you might also have that box might be pretty heavy. All right, that would indicate we have a pretty heavy, I'm going to choose a different color. All right, so we have a pretty heavy weight force acting on that object. So here's our weight force, but not quite as strong as the force applied, right? Our weight force it's there. I meant to draw a G, right? It's there, but not enough for us to not be able to overcome that with our applied force. And remember, our weight force acts directly down on our object in question. right? Our normal force, remember your normal force is perpendicular to that surface. So our normal force is actually going to be, oh, and I totally drew that with the wrong tool. Our normal force is actually going to be at a right angle again to that surface of the ramp there. All right. So that's our normal force. So I'm going to label that Fn. And finally, we have the force of friction. Let's say it's a pretty slippery ramp. So I'm going to highlight normal force in green. Our force of friction is pretty negligible, meaning that it's really not affecting us that much. So we're still able to overcome that force of friction. So it's going to be a pretty short arrow, indicating that that force of friction is not too much for us to handle. All right, so this is an example of a complete free body diagram for that box. All right. So that is what a complete free body diagram looks like. Now, if we wanted to calculate the total amount of force that all of these forces are having on this particular box, this is what we call the net force. So this is another vocabulary term for you all. And so net force is the total magnitude and direction of all of the forces acting on an object. So total magnitude and direction of all of the forces acting on an object. I'll zoom out a little bit so y'all can see that definition here. So if we are calculating the net force, we use the variable capital F for force and then subscript net, the subscript word net, to indicate that is our total amount of force acting on those objects. Again, our unit for that force is newtons, and the equation for calculating net force is F net is equal to the first force plus the second force plus the third force, and so on. So in this example here for this box, so right here in this example, if we were calculating the net force on the box, so here I'll redraw my free body diagram. We've got F net, or excuse me, F normal. We've got our force applied. We've got force of gravity. And we've got our friction force. So maybe let's say our force of friction was, or actually, let's restart. So our F net of all of these forces would be equal to the normal force, Fn, plus our force applied, so normal force plus force applied, plus our force of gravity, or our weight force, plus our friction force, force of friction. All right, so maybe F net, excuse me, maybe our normal force, right? Remember, we're looking at these forces in an XY coordinate plane. We've got our positive Y values, our negative Y values, our negative X values, and our positive X values. So F normal is, we'll say that's maybe positive 10 newtons. And then we add that to our force applied, which might be a positive 20 newtons. Add that to our weight force, and our weight force is actually always going to be negative because it's always pointing downward in that Y direction. So maybe negative 10 newtons. And then finally, we would have our friction force, and let's say our friction force is, I don't know, maybe just -2 newtons. Okay, so these forces, since they're in the same direction, and I know that they're at a bit of an angle, but we'll ignore that for now. But these forces, since they're basically in the same direction, our normal force and our gravity force, they're actually going to cancel out, right? +10 plus -10 is equal to 0. So then all we are left with is the F net is equal to +20 plus -2 newtons. +20 plus -2 is -18 newtons. So that would be one way of solving the total amount of, and that is not -18 newtons, it is +18 newtons. That is one way of calculating our total amount of force acting on an object. And again, technically, we would need to factor in the fact that this our weight force is not completely lined up with our normal force, but we're going to say that it is close enough to being what we call negligible. So we can kind of ignore that for now for purposes of simple math. All right, so when two or more forces are balanced, the net force is between them is equal to 0. So we actually saw that happening here. Like I said, any object, we just have a box sitting on a table. Here's our box, here's our table, right? That table or that box is exerting a force, its weight, which is our force, down on the table. But that table is exerting an equal normal force upward to balance out that weight force. Otherwise, that box would just fall straight down to the ground. So these forces are balanced forces. Now, in unbalanced, so balanced forces meaning that if those forces are balanced, that object is at rest, or it might be a constant velocity. Maybe we have an object, a box sliding across a room here, right? So we have that box sliding across a room at a constant velocity. So if it's at a constant velocity, it is not accelerating, meaning it is still balanced. I'm going to say at rest. So these are examples of balanced forces. Now, an object would be accelerating if it was experiencing unbalanced forces. So if an object is moving down a ramp, right, maybe that ramp has a little bit of friction to prevent it from sliding super fast down, but you gave it a really good push down that ramp. That's unbalanced force. Meaning that the force of friction is not equal to your force applied, meaning that object is accelerating. Okay, so that kind of wraps up our discussion about forces and net force and free body diagrams and how to calculate all the forces acting on an object. Remember to write your summary, about a 1 to 2 sentence, trying to answer that essential question in your notes. And I look forward to talking about this in class.